our next speaker is Georg Hammerl, who will present his work where he, as far as I understood, compared the performance of certain Trilinos solvers to solvers in other commercial finite element codes. And I'm very eager to hear your assessment and your thoughts.
Okay, Matthias, thank you very much. I'd like to thank the organizers that I'm allowed to speak here. The work I present was produced together with my colleague Ingo Scheider. And as Matthias mentioned, I'll talk about a transition phase that we've currently have started. We're using a commercial code, and we have the possibility to use the in-house code. And at some points we struggle a little bit, or we have challenges. And this is something that I'd like to talk about today. So let me just give a short outline what I'll be talking about. First, introduce Hereon, where I'm working at, give the motivation, so the application that I brought with me today. Next, I'd like to start my comparison. On the one hand side, there's ease of use, so how much user intervention is necessary. And here combine the commercial code Abacus and our in-house code. And on the other hand, it's the performance that we see with both FE solvers. And as already was done by Peter in the previous talk, I'd like to point out where we're using Trilinos and where we see potential for further and in deep use of Trilinos. There's something, maybe we have a small discussion at the end, which might be very interesting for us. Finally, I'd like to conclude my presentation. So Helmholtz Association is a German research association. It's distributed all over Germany, and I'm part of one of the northern ones. It's the Helmholtz-Zentrum Hereon. Our main location is in Geesthacht, it's close to Hamburg, and I'm part of the Material Systems Modeling Institute. In total, there are at Hereon 1,100 employees. So it's, I would call it medium size for Helmholtz centers. The problem that I'd like to talk about today is composite material, and it's special material that targets on high stiffness, high hardness, and high strength at the same time. And it's a composite of a ceramic nanoparticle. Nanoparticle means something around 20 nanometers in diameter, and they cover a large volume content, so they're very densely packed in a crystalline arrangement, and they're surrounded by an organic layer, and it's very thin, it's just 2 nanometers, so everything is very small. Here on the left side, we can see a scanning electron microscope view, and it's very regular, as mentioned, this crystalline arrangement. And here you can see the model that we assume, so our spherical particles, they're surrounded by this touching organic layer. And here they're combined together. And this is here on the right side, the FE model that we derive here and construct in, so to say, arbitrary fashion. So we place these particles slightly randomly, and so fill the whole representative volume element that we analyze. For my comparison, I've used 2 different setups. One here shown on the left side, it's called here the small model. It has something around 650,000 degrees of freedom. So it's 1.1 million tetrahedral elements, so TET4 elements. And on the other hand side, we have finer discretization. So we end up with something around 17.5 million degrees of freedom, and it's more than 4 million 10-noded tetrahedral elements. Here the material properties are given. So it's, I would say, 3/4 of the Young's modulus of steel, the particle inside. and the organic layer that is around, it's 13 times less stiff, and it's closer to incompressible than the inner material. Actually, it's a very trivial setup, if we're honest. So it's 1/8 of my representative volume element that I'd like to model. So 3 times symmetry boundary conditions. And we pull here on the upper side by 1 nanometer, and the geometry is 76 nanometers in length. But as we actually thought this is a trivial example, we had more problems than we expected, which I'd like to show in several of the next slides. So in the past, Abacus was used at the Institute for a really long time. UMAT, so user subroutines were written, and there's really a lot of experience with these implementations and worked very well. And now we started a transition phase towards our in-house FE solver. So the head of our institute brought with him an in-house code that is developed at the University of Munich in the past. And we follow up these developments, and we're allowed to use it. And we see here a lot of opportunities. That's the reason why we'd like to use it. But also, of course, we face challenges. And so far, there's less knowledge, especially about the mathematical background, especially of linear solvers. Of many coworkers, they were really focused on this material modeling aspect, writing the user subroutines, and the main work was done by Abacus. And now we have to take our hands on these parts too, and it's some challenge for us to really get the full potential that is available in the linear solvers, especially here in the Trilinos solvers. So there's a huge variety that is available, and of course we aim on good conversions, should be fast. We're running the problems on HPC systems, so it's also a question of time and money in the end, and energy. So it's more or less the same for us. And here the question is how to get to a fast and good solution. If you have a look on Abacus, which we've used so far, to be honest, the documentation is very sparse. They just tell us there's an iterative linear solver in use. It's a precondition Krylov method. At some point it says that it is CG that is used. And at one point, the precondition is described as PAMG. So I assume some multigrid method, but there is actually no more detail that is directly obvious. And Abacus supports a hybrid MPI, a thread-based parallelization, which is quite nice. At the same time, the user intervention is very limited. There are just 2 options that can be triggered by the user. So on the one hand side, the relative tolerance for convergence, which is set to, I would say, a reasonable default value. And on the other hand side, it's the maximum number of linear solver iterations set to a default of 500. That's actually already everything that can be done within Abacus. If you have a look now, here just a short overview of our in-house code. And here I'd like directly to point out where we are using Trilinos packages. On the input side, it's the Techos parameter lists that we're using. The load balancing is done with the Sultan package. And we have a look here on our the simulation, the calculation itself, especially on the solver side, we rely exclusively on the Trilinos solvers. So at some point we use the Knox linear solver and nonlinear solver, and mostly it's still the ETSIG-00 linear solver for iterative problems. Some parts we use Bilus, especially if we have several right-hand sides. And Bilus is of course interesting. And the preconditioning packages ML, MULU, mostly for contact problems. So I will focus here on ML exclusively today, and IFPEG. And on the physics operator side, it's at some points intrepid and shards that is in use. And as the presentation before, everything is still also based on the Petra stick. So there is what Matthias has mentioned, this transition in front of us to get to the future here. Let me just briefly show you the parameters that I've used for my linear solvers, so for my comparisons. And another part of the documentation of Abacus, I found ILU in use. So the Aztec package with TMRS as Krylov method, and the ILU preconditioning with the fill limit of 2. Iterations and tolerance set to the same limits as Abacus usually does. Then I had a second variant for the solver settings that we tried for our small and large model. It's so the same here on the left side, except that ML is used as this preconditioning method. And here on the right hand side, we can see most of the relevant parameters, especially here the smoothers, Chebyshev polynomials on the fine and medium levels, and the KLU for the coarse level. And here with the corresponding smoother times and maximum of 5 levels, and maximum coarse size. So when the KLU is used is 1000. Last version, so I just switch forth and back that you can see what differs. It's just here on the right hand side on the bottom. Everything's the same except that we use symmetric Gauss-Seidel here is smoother and reduced smoother times. So all the other parameters are identical. And if now I look on the timings that we obtain, so here in the first 2 rows, you can see Abacus in use. The last 4 are our in-house solution. And if you just have a look at the direct solver, and it's from 8 to 16 up to 128 processes that we use in our cluster. If you have a look here at the direct solver, in parentheses, it's always the number of Newton iterations. So 1 Newton iteration, direct solver, so it's only MPI based. So we did not use here the hybrid version of MPI and thread based to have a more fair comparison. But we can see timings here less than a minute for this problem, which is quite fine. There's, I would say, no real improvement, especially here it's getting worse, but maybe this is already due to the problem size that's just too small for the number of processes that we're using. If we have now look at the iterative solver, then we can see here, improvement, especially for the larger numbers. Why this, I would call it gap here, is we haven't had a look in detail, and actually it's hard to figure out what happens inside Abacus. So, but we see here these numbers, it's a clear improvement compared to the direct solver. And what was a little bit surprising to us, if you have a look at our direct solvers, so it's a SuperLudist that we used. We have timings that are way higher, so this was a little bit surprising to us. At the same time, we're using the direct solvers just very seldom, so it didn't matter that much to us. The more interesting numbers are actually on the 3 rows on the bottom. So with the iterative solvers, this is, so to say, the standard that I'm used. So here, it's this version with the ILU preconditioning, this fill level 2. You can see here always 1 Newton iteration, so this is very good. It's actually, to be honest, a linear elastic problem. It's just about the 2 materials that are included. So this is fair to assume that it converts very, very fast. And also the prescribed displacement is rather small compared to the geometry. So this is in a good agreement what we expect. Again, here the numbers are getting slightly higher at the end, telling us that the problem is just too small for the number of processors. So this is fine what we see here. And what was very good to see for us, that we came at least on the same level in Abacus and also have improved here a little bit compared to what our commercial solution provided to us. Next, here's the GMRS with the AMG preconditioning with the Chebyshev polynomials. Here also timings go down, everything's fine, and then we end up with a solution better than our commercial solution. So again, we're happy. And the last one is with symmetric Gauss-Seidel. And here it's quite interesting. We didn't expect this. So the number of Newton iterations increased a lot. And so the timings, of course, are no longer that good. And that's a bit of our problem. We are not that deep in the mathematical background. And we usually do not run the full table in order to find out which variant we should use. So this is one of the questions that I'm interested in. What is a good way for starting guess which version to use, and how can some of my colleagues that have even less knowledge than my colleague Ingo and me be prepared that they have a chance to run their simulations, which are of course more complex than this linear elastic, let's call it toy problem. It's just a little bit about the size, but the mathematics, physics are not that difficult actually. And if you have a look now at our large example, so we skipped the 8 and 16 processors calculations. We skipped the direct solver for Abacus because it just took too long, more than an hour. And we focused here on the iterative ones. And it was quite interesting. Abacus gave more or less all, independent of the number of processors, the same timings, always 2 Newton iterations. And here we can see these numbers, actually one of the smaller ones here in the full table. So if you have a look here on our in-house solution with EuroTUG ILU preconditioning, we can see timings are way higher. There's just 1 Newton iteration, so this is very good. But the solver takes actually a long time compared to our commercial solution. If you have a look now at the multigrid method, it was a little bit surprising. So timing is less than LU, which was something that I would expect. Here, surprisingly, the number of Newton iterations increased to 2, although the timing is still very good. And here with the largest number of processors, we have a number that is competitive against what we are seeing in Abacus. So this is a solution that we would be actually fine. And just to give you the last row, this was very surprising. I didn't expect here the symmetric Gauss-Seidel to be that bad in convergence. So several Newton iterations didn't converge, and the simulation was just aborted after more than an hour. So here's now no clear timing. With 64 processors, everything was fine. Timing is great. And if you again increase the number of processors, we see here again way more Newton iterations. A little bit more, or look in detail told us that the problem is just ill-conditioned. We actually didn't expect this. Might be the reason that several of the elements are distorted and have Jacobians close to 0. But actually, geometry should not be that complex, and physics as well. So it's purely linear and elastic what we're running. So here we were a little bit surprised, and again, so for us the question, it's nice to get this sweet spot, but what is a good way to figure out which version I should use if I do not have the full table available. Is it just the parameters that are not that good? Is it the wrong method? So should I read a good math book? Should I talk to a person with experience? I'm not sure. Do more Trilinos users challenge these, let's call it starting problems? How do others approach here to get to the necessary knowledge to figure out a good solution for one's problems? And if I think about the previous presentation, having plasticity and so on, how is there a chance to get nice solver settings? We have also thought where it would be possible or maybe interesting for us to extend the Trilinos usage within our in-house code. And something that Matthias has already mentioned, we need to leave the CPetra stack and would like to switch to TPetra. And this then opens the path to COCOS, because we're in the Helmholtz-Association have the possibility to run, for example, simulations on the Jülich Supercomputing Center at Tech University of Munich, where I'm also affiliated. It's possible to run here in the Leibniz-Rechenzentrum in Garching. So we have several possibilities for really large systems that we can run our problems. So this seems to be very interesting for us, but it's more on the longer run. This might be interesting. We have some refactoring in front of us. And our code relies, for example, on several time integration schemes and several places in the code. It's not very well written. So here we might have the option to go here to the Tempus package. And one big problem that is the scaling of our discount potential left. And here one option would be this what a good way might be if there are opinions or experience from other users. This might be very interesting to us, and if we can discuss after the presentation, this might be very helpful for us. So let me conclude. We're currently in a transition phase from the commercial FE solver Abacus to our in-house solution, which is Trilinos based. This gives, of course, opportunities. We can tune now the solver that hasn't been possible in the past. But it's, of course, a challenge, especially for those who are experts in the modeling, material modeling aspect, but they're not in depth with the mathematical aspects. It's really a challenge for us how to tune the solver, and this ease of use aspect that we're used from Abacus, how to get there with the Trilinos packages. And as on the last slide shown, there are possible extensions, and here it might be interesting for us if there are some recommendations which path we can go. So thank you very much for your attention, and if there are any questions, please let me know, and hope that there is a little bit on discussion on the topics that I've thrown up. Thank you.